Hi, welcome back. In this video, we are going to discuss about the CPU. The CPU is short for the Central Processing Unit. And as we mentioned in the previous slide, the CPU basically including two parts, the control unit and the arithmetic logic unit, ALU. The control unit will direct and coordinate operations in the computer. And the ALU will perform arithmetic, comparison, and logical operations. So this is the John von Neumann architecture. We have the CPU will talk to the memory, and then the memory will connect the input and output devices, and at the same time, the memory will store the data in the storage. Let's look at the ALU first. So the ALU will perform the basic arithmetic operations such as addition, performs the logical operations such as AND, OR, and NOT. Most modern ALUs have a small number of special high-speed storage units called registers. So the registers will hold data to be processed immediately, while the main memory will hold the data that will be used a little bit later. The control unit will send out control signals to all the devices in the computer. And there are two special registers in the control unit. The first one is called the IR, the instruction register, and second one is called the program counter, PC. So these two registers are very important because the CPU will use these two registers to fetch and execute the instructions. And different components will be connected by using the bus. A bus is a collection of wires to transfer the data. Now let's look at the fetch execute cycle, which is a very important concept in the CPU. So in the fetch execute cycle, the first step is to fetch the next instruction. So after you fetch the instruction, you're going to decode the instruction. And then you're going to get the data if it's needed. I mean, like some of the instructions need some data, some of the instructions doesn't need some data. And then if you execute the instruction, and then we'll go back to the first step, which is fetch the next instruction. So it will make this a loop. Before we go into the details of the fetch and the execute cycle, let's look at the memory first. So the memory is a collection of cells, and for each of the cell, it will have a unique physical address, just like the picture shows here. So the right side is the memory, and the left side is the address. So for example, this is the address for this cell, and this is the content, in the main memory. So the main memory is a collection of cells, and for each of the cell, it including 8 numbers. And the number is binary, means we only have ones and zeros. So for each of the cell, it has 8 binary numbers. Now let's look at the fetch and execute cycle. At the bottom of the picture is the main memory. Suppose we have 2 memory cells that stores 2 instructions. The first instruction is 1 plus 1. And the second instruction, let's say, is 1 plus 2. And there are 2 physical addresses for these 2 cells. Let's say if the first address is 0, 0, 0, 1. And the second address for the second cell is 0, 0, 1, 0. So now let's try to run this program. So first of all, the program counter register will be set to the address of the first instruction. Okay, so the address is 0, 0, 0, 1. And then the CPU will try to fetch the instruction from this location. Okay, and if it will fetch the instruction from the main memory, which is here, okay, to the IR register. And then the control unit will try to decode the instruction. So after it decodes the instruction, it shows that this instruction is an addition. And then it will try to put the data into the register. And then go to the third step. And the ALU will use some general purpose register to hold the data. Let's say we have two registers here and here. So the first register will hold 1, and the second register will also hold 1. And now in the IR register, the operation is addition. So now the ALU will try to execute the instruction, which will be the addition of 1 plus 1. So this instruction will be finished. And then the CPU will go to fetch the second instruction. It will automatically update the PC register by changing the address from 0001 to 0010, so which is the address of the next location. And then it will fetch the instruction, which is 1 plus 2. And then it will decode the instruction, and then it will load the data to the general purpose registers, which is 1 and 2. And the IR now is also addition. So it will execute 1 plus 2, and then it will try to fetch the next instruction. So this is the fetch execute cycle. So with this cycle, the CPU will try to execute all the instructions in the program until the end of the program. And here shows you what kind of components inside the system unit. So basically, it has the processor, memory, different type of cards and ports, drive base, power supply. And the most important circuit is called the motherboard. And as you can see from the picture, all of the components will be mounted on the motherboard. So the motherboard is also called the main board. The motherboard provides different type of slots so that different components can be plugged into the slot. Like here we have the memory slots, and the CPU also plugged on the CPU slots. And we also have some other slots here so that different cards can plug on the motherboard. And the key part of the CPU is called the chip. As you can see from here, so this is the chip, and here's the processor. And here shows you how a processor are made.
Microprocessors. They have become indispensable in our modern world and can only be produced in clean rooms under the most stringent of conditions. Sand is the basis for most microprocessors, which has a high silicon content, but also contains other elements such as oxygen and calcium. Through heating and other processes, silicon is extracted from sand and cast into blocks. Such a block has a high level of purity and is called ingot. The block is cut into wafers of the desired thickness of anywhere from 0.5 to 1.5 millimeters, depending on their intended use. The wafer is then polished and subject to rigorous inspection. If the wafer passes the subsequent inspection, the first step of production begins, which is called front end of line. Here, the integration of transistors takes place. In the first step, a layer of silicon dioxide is laid down on top of the wafer, upon which a layer of silicon nitride is applied. Then, a very thin coating of photoresist is applied. A spin coating technique is typically used to spread the photoresist over the surface. In the next step, a prefabricated stencil composed of transparent glass and opaque chrome is projected onto a lens. The lens reduces the size of the stencil pattern. The photoresist becomes soluble wherever it is exposed to UV light. The dark areas here indicate the regions that are to be removed. These can be removed through the application of an appropriate solvent. Let's look at the surface a little bit closer now. The solvent uncovers part of the silicon nitride layer which lies beneath the photoresist. The application of corrosive liquids etch away the desired regions of the other layers in order to expose the silicon. Finally, the cleaning of the photoresist and a further chemical etching of the silicon regions. Another layer of silicon dioxide is then applied, which will serve as insulation between the transistors. Etching and grinding processes expose the silicon underneath. Photolithography is used once again in the process of doping the silicon regions for the purpose of protecting the regions which are not to be doped. The silicon regions are treated with either N or P-type doping through ion implantation. This example is one of an N-type doping. The photoresist can finally be removed. Looking at the doped regions, it can be seen that the implanted electrons are able to move freely and thus are able to carry electrical current. Finally, the creation of the gate dielectric, in which photoresist will be used to make source and drain areas through the implantation of foreign atoms. This is the fundamental structure of transistors. At this point, the front end of line is completed. From here, the back end of line begins. The back end of line begins with the application of undoped silicate glass in which holes for connection purposes are created. These will then be filled with tungsten and the electrical connections between the transistors will be created. The end result is a wafer full of chips which will be separated from each other using a saw and then embedded in a housing. Through the process of bonding, the chip is attached to the contacts within the housing. A housing cover serves as protection from external elements such as dust. The processes shown in this animation are greatly simplified. The production of a microprocessor can require more than 100 individual process steps and can last for many weeks. Today, a simple microprocessor can contain several billion transistors.
So in this video, we know the general process of making a microprocessor. So actually, inside of the chip, there are billions of transistors. So the transistor is the key part of the chip. So here I have another video to show you how the transistors will work.
Modern computers are revolutionizing our lives, performing tasks unimaginable only decades ago. This was made possible by a long series of innovations, but there's one foundational invention that almost everything else relies upon: the transistor. So what is that, and how does such a device enable all the amazing things computers can do? Well, at their core, all computers are just what the name implies: machines that perform mathematical operations. The earliest computers were manual counting devices, like the abacus, while later ones used mechanical parts. What made them computers was having a way to represent numbers and a system for manipulating them. Electronic computers work the same way, but instead of physical arrangements, the numbers are represented by electric voltages. Most such computers use a type of math called Boolean logic that has only two possible values, the logical conditions true and false, denoted by binary digits 1 and 0. They are represented by high and low voltages. Equations are implemented via logic gate circuits that produce an output of 1 or 0 based on whether the inputs satisfy a certain logical statement. These circuits perform three fundamental logical operations: conjunction, disjunction, and negation. The way conjunction works is an AND gate provides a high voltage output only if it receives two high voltage inputs, and the other gates work by similar principles. Circuits can be combined to perform complex operations like addition and subtraction, and computer programs consist of instructions for electronically performing these operations. This kind of system needs a reliable and accurate method for controlling electric current. Early electronic computers like the ENIAC used a device called the vacuum tube. Its early form, the diode, consisted of two electrodes in an evacuated glass container. Applying a voltage to the cathode makes it heat up and release electrons. If the anode is at a slightly higher positive potential, the electrons are attracted to it, completing the circuit. This unidirectional current flow could be controlled by varying the voltage to the cathode, which makes it release more or less electrons. The next stage was the triode, which uses a third electrode called the grid. This is a wire screen between the cathode and anode through which electrons could pass. Varying its voltage makes it either repel or attract the electrons emitted by the cathode, thus enabling fast current switching. The ability to amplify signals also made the triode crucial for radio and long-distance communication. But despite these advancements, vacuum tubes were unreliable and bulky. With 18,000 triodes, ENIAC was nearly the size of a tennis court and weighed 30 tons. Tubes failed every other day, and in 1 hour, it consumed the amount of electricity used by 15 homes in a day. The solution was the transistor. Instead of electrodes, it uses a semiconductor like silicon, treated with different elements to create an electron-emitting N-type and an electron-absorbing P-type. These are arranged in 3 alternating layers, with a terminal at each: the emitter, the base, and the collector. In this typical NPN transistor, due to certain phenomena at the PN interface, a special region called a PN junction forms between the emitter and base. It only conducts electricity when a voltage exceeding a certain threshold is applied. Otherwise, it remains switched off. In this way, small variations in the input voltage can be used to quickly switch between high and low output currents. The advantage of the transistor lies in its efficiency and compactness. Because they don't require heating, they're more durable and use less power. ENIAC's functionality can now be surpassed by a single fingernail-sized microchip. containing billions of transistors. At trillions of calculations per second, today's computers may seem like they're performing miracles. But underneath it all, each individual operation is still as simple as the flick of a switch.
So after studying the general process of making a processor and how the transistors work, let's look at the evolution of the CPU. We just take Intel as an example because Intel actually perfectly reflects the development of the CPU. In the past several decades, the microprocessor has been improved rapidly. In 1971, the first single-chip microprocessor is made, and the name of the processor is called 4004. It was only a 4-bit processor. And in 1978, the first 16-bit CPU was made, and the name is called 8086. And then we have the 8286, 386, 486. From 16 bits to 32 bits. And then we have the Pentium series. So we have Pentium, Pentium 2, Pentium 4, Pentium M, Pentium D, and then we have the Core series. So we have the Core 2, Core 2 Core, Core i3, i5, and i7. And then we now have the i9. And you may see the architecture of the CPU is called x86. That's because it's from this CPU. Because all of them use the 86. So the name of x86 actually represents the Intel CPU architecture. So if we draw a figure of the production year and the number of transistors of every of the processors, we got this diagram. It is called the Moore's law. It says that for every 18 months, the number of transistors will double. So this is called the Moore's law. So what are the factors that will affect the performance of the CPU? It's basically including 4 factors: the clock rate, the word size, the cache, and the instruction set size. So the clock rate, you can also call it frequency. It measures the speed of the CPU for data transport and the instruction execution. As you can see from the bottom image, the frequency of the processor changed from 2.9 GHz to 3.4 GHz. The word size refers to the number of bits the CPU can manipulate at one time. So as you can see from the previous processors, some of them we call it 16-bit CPU, some of them we call it 32-bit CPU. That is the word size of the CPU. So of course, if a CPU can manipulate more bits, it can actually process more data. So the cache is a special high-speed memory that gives the CPU more rapid access to the data. So instead of access the data from the main memory, the CPU prefers to use the data in the cache because the speed of the cache is far faster than the speed of the main memory. For example, in Intel i5 has 3 different type of caches: the level 1 cache, level 2 cache, and level 3 cache. It has 32 kilobytes of the level 1 cache, and it has 256 kilobytes for the level 2 cache, and have 8 megabytes for the level 3 cache. And here shows you the AMD CPU. It also has 3 levels of cache. So when an instruction calls for data, the CPU will first check to see if the data is located in the cache. If the data is in the cache, the CPU will take the data from the cache instead of the memory. So here the RAM means the primary memory, the main memory. So if the data is not even in the main memory, the machine will try to load the data from the hard disk into the main memory. So this is about the CPU, and we are going to introduce the primary memory, and you're going to distinguish the RAM, ROM, cache, register in the coming slides.